All right, so this is our homework, and we talked about how x starts at 8 and it's approaching 2. So by the time we get here, x starts at 8 and it reaches 2. And as x approaches 2, we look to see what the y's were doing. And based on what you guys plugged in, you should have ended up with y starting at 64, 49, 36, until we end up with y approaching 4. Then I had you guys calculate the slope. The slope was from these points. Like we didn't get into this, so I can say that. Like 864 from this point to that point, which was 2, 4. And we were finding the slope, and we got 10, right? And as we worked our way down, we found that that also was approaching 4. Okay. So as x approaches 2, y approaches 4, and in this case, this is just coincidence, so don't try to make any connections that aren't true. But in this case, the slope is approaching 4 also, okay? So as x approaches 2, the y value and the slope are both approaching 4. And you could look at the graph here geometrically, you can kind of see this. You know, the slope starts really steep, and as I make more and more lines that get closer and closer to this point, it's getting smaller and smaller. And now we can't actually calculate the slope at that one point. Why? Because to calculate a slope, what do you need? You need 2 points, but there's only 1 point there. And what would happen if you tried to calculate the slope from one point to itself? What would you get as a fraction?
0 divided by 0.
Which is, you can't do that, right? But that doesn't mean there's no answer, right? In this case, that doesn't mean there's no answer. It just means that our slope formula doesn't work for us. Because we could tell by looking at these tables that there is a slope. It's getting closer and closer to 4. So that's interesting. The second part of your homework was the same thing all over again. So I hope you guys enjoyed that repetitive mind-numbing process. But the difference was we were approaching, instead of coming from x equals 8 and working down to 2, we started at x equals 0 and worked our way up to 2. But either way, what was your y value approaching? It was still approaching 4. And what was your slope approaching? Still 4. Okay, so it doesn't matter whether you're coming from the right or left. It's approaching the same slope on both sides. So it seems like there is a slope at that point, and the slope would be 4. It's the slope at 1 point. So the slope at a single point is what's known as an instantaneous rate of change. Okay? Because instead of finding the change over 2 points, which is like an average between them, you're finding the slope at 1 point, and that's called an instantaneous rate of change, the instantaneous slope. This whole beginning of this chapter is called derivative rules. A derivative, you don't need to write this because I printed it for you, but a derivative is an equation. And it's an equation that if you take that equation, you plug a number in, it will tell you what the slope at that 1 point is. It will tell you what the instantaneous rate of change is at that point. So for instance, for the one on your homework, what was the equation of that function? What was it? It was y equals what?
X squared.
It was y equals x squared. For y equals x squared, the derivative function for that is y equals 2x. You'll know why by the end of tomorrow. But for now, just take my word for it. The derivative function for this is y equals 2x. This is an equation that will tell me the slope of this function at any point. What point were we approaching for x again? 2. So if I plug in 2 here, what do I get? Tells me the slope at that point. So we don't have to use that mind-numbing table process to guess anymore. So this whole chapter is about teaching you guys how to find the equation for any function you want that gives you the derivative, which is an equation that helps you find the slope at any one point, any instantaneous rate of change. Does that make sense? So I'm gonna say all that again in our lesson, but I'm just pulling our homework into what we're talking about today. So go ahead and pass forward your homework, and I'm going to pass out today's notes to you. Okay, so by the end of this lesson, you guys are going to be able to tell me what an average rate of change is. You're going to be able to tell me what an instantaneous rate of change is. you should be able to kind of also elaborate on what they have in common and what's different about them. You should be able to define for me what a derivative is. And then most of our well, no, that's not true. About half of our discussion day is really just going to be about how to read math, because you're going to be learning some new symbols, and I want you to get used to seeing those symbols and what they mean and how math is written. We might bite into this for a second, but we're going to actually finish that one up tomorrow. So lesson 1.1 is going to be 2 days long. Okay. Tonight you will have 2 homework assignments. One is a worksheet 1 through 6, which will be due tomorrow. The other one is FRQ practice. That one, it won't be due until Monday. So while I'm on that topic, why don't I pause the lesson for a minute, and let's talk about that one really quick. FRQ practice. Does anybody in here not know what an FRQ is? We know what those are? Okay. So basically I'm picking questions from previous tests that are related to the stuff that we're learning right now, and I'm letting you guys practice it. And in the beginning, they'll seem a little like that's hard and difficult, but you know, after you see how to do it, you're like, oh, okay, I get it. It's not a big deal. So here's my suggestion. Here's one. It's only one problem, okay? And here's my suggestion for any FRQ that I assign. This is where you're going to get your most bang for your buck, okay? Try it on your own first. Okay, that's my suggestion to you. Always try it on your own first. Go as far as you can. After that, I'm going to upload a helpful hint video for you. I'm not going to tell you how to do this problem, but I'll tell you the things that I would think that you'd probably be stuck on, and then go back and try it again. After that, go on YouTube. You can actually look up the answer. They've got people that have worked all these things out. You would type in what FRQ this is. This is the FRQ 2004 question number 1. So if you type in Calculus AB FRQ 2004 question 1, you'll have to fast forward until you get to part D. Okay, but they'll work it out for you. Another thing you can do is you should go on Google or some search engine and type in Calc AB FRQ 2004 scoring guide, and you could see how they give points, because that's interesting too. You'll be surprised. You'd think they give a point for that, and then something else will be like, why didn't they give a point for that? And after you start studying how they actually give points out, you'll see patterns, and eventually you'll be able to predict. And that's important, you know. Knowing math is one thing, but getting a score is another, because how people score is subjective, right? So you need to know how to read the mind of these graders, and they have very specific rules that they stick to, so you want to get used to that. So that would probably take you about, you know, maybe 20 to 30 minutes, you know. The other homework assignment give me about 30 minutes, so tonight you'll be looking at about an hour. But mind you, this is the easy time. I told you in this class, you're looking at about 1 to 2 hours a night. Okay, so that's not uncommon. I'm going to be giving you one of these every night. Okay, well, not every night. Every night this week I will. I'm going to give them to you whenever I can. Sometimes there's just not an FRQ that goes with what we learned, so we won't. But that's what we'll do. So that's my suggestion. Try it on your own. Check out the video for helpful hints. Then go on YouTube. Then see how it's graded. Could you just jump to step C and look it up on YouTube and write down the answer and be done in 5 minutes? Yes, you could. I would never know the difference, but that's okay. You're not trying to impress me. You're trying to pass your AP test. So if you do that, you'll probably be hurting yourself, just so you know, because you really need to know how to think through these problems. Okay? So, yeah.
The FRQ paper or the other one?
Good question. So both of your homework assignments tonight, the one that's due tomorrow and this one, which is due on Monday, they're going to be uploaded on Google Classroom as a document. You can write everything on your own paper. You can print these out and write on there if you want to. I wouldn't encourage that. I think that's a waste of paper, but some people like to, so you can. That doesn't matter to me either way. By the way, the worksheet that you're doing tonight for homework that's due tomorrow, which is based on the stuff we're learning in class today, that is, you're only going to do numbers 1 through 6. There's like 12 or 13 problems on there or something. You're only going to do the first 6. We'll do the other ones tomorrow night. Okay? Any questions? All right. And don't forget about your math meme. That's also due next Monday. All right, so now we got homework out of the way. Let's go back to this. So like I said, we're talking about what's average rate of change, what's instantaneous rate of change. We're going to learn how to read math, and then we're going to look at some derivative rules.
You want the math using physical copy or digital?
I would like a physical because I want to put them on the wall, and all year long I kind of go around and skim them and learn about you. So I'd appreciate it.
Okay.
All right. Today there's not very much process, but there's a lot of concept. In other words, I'm going to be telling you what a lot of things are, but you're not going to be calculating almost anything today. Today is just laying the groundwork for what a derivative is. So let's go ahead and we'll do some math work tomorrow. Let's go ahead and start up our talk thing here. This is distance, 100, and this is time or hours. I'm going to say 2. Let's say that a vehicle started at 0, 0 and ended up here. What is the speed of that vehicle? $50 miles an hour. How did you get that?
So it goes over the miles in 2 hours, and that means that the slope is 50.
Okay, good. So slope is speed. Okay, that's not technically true, but for today that's good enough. Slope is like the speed of your function, how fast it's changing. In other words, it's also known as rate of change. In this case, the speed of that vehicle is, as Brody said, it's 50 miles per hour. Why? Because as you guys know, speed is distance over time, right? And what's the distance traveled by that vehicle over a time period of? And so 100 over 2 is 50, and we have miles on top, hours on bottom. That's miles per hour, right? So there's your speed. That's your rate of change. Okay? And I'm assuming the car has been going the same speed the whole time, right? What Brody told me was really the car's average rate of change, because really when you go for a drive, the speed of the car changes, right? But if the car overall went 100 miles in 2 hours, we'd say, okay, on average it's going 50 miles an hour. Is that fair to say? Now, if I drew a straight line like this, okay, imagine that being straight. Where will the car be at after 1 hour? Nifty. And that's, if I make a straight line, that's because I'm assuming the slope is always the same. It's over 1 and up how far? So 50 over 1, rise over run, right? Or from 1 to 2, and then from 50 to 100, still has a rise of 50 and a run of 1. It doesn't matter what 2 points you pick, you're always going to get 50 over 1. Even if you did this, you get 100 over 2, but that's still 50 over 1, right? The slope is always the same. So in this case, I'm telling you the car kept a steady, they must have had it on cruise control, right? It didn't change, it was always 50, no traffic. Okay? But what's possible is maybe it did this instead. Change colors here. Can you tell me what's happening here as opposed to here? Like, what's the difference between those two parts of the story here in this car going? Yeah?
The car's accelerating.
Okay, good. What were you going to say, Marcos?
I was going to say when the line is straight, it's keeping a constant.
Good.
Line, it's keeping a constant speed when it's going like this. It's like it's getting up over time, and as the further it goes, the more distance it travels, the longer it takes.
Good. So you're both saying it's accelerating as increasing, right? Because technically, you could be decreasing your speed, and that's, in the world of physics, that's still considered acceleration. It's just a negative one, right? But how do you know that the speed's increasing and not decreasing by looking at this graph, Andy?
It looks like an exponential graph. So
Okay.
if it goes in a curve to the right side up, that means it's exponentially growing.
Good. Do you guys remember the word for graphs that bend up like that? That's a type. It's a type of one. But when graphs bend up, we say that the graphs are starts with a C. Concave up. Ring a bell? No. All right. So that's okay. But check this out. If I were to do an average slope from 0 to 1, there's my slope, right? Now, what if I did an average slope to 1 to 2? How would you compare those two slopes? That's right. The second slope is steeper, right? That's a bigger number. So the slope got bigger. In other words, the car's speed increased. Does that make sense? So what we have here is when you have a bending line, you have a changing speed. We talked about this a little bit yesterday. And in that case, it still has an average rate of change of 50 miles an hour, but every point along this curve has a different speed. It's constantly changing. Okay? So, so let's go ahead and talk about average rate of change versus instantaneous rate of change in a more raw fashion here. So we have a curve, right? If I were to connect these two dots with a line that connects two dots on your curve is what's called a secant line. Secant line. How many dots are there? Two, right? It's kind of like second, first and second point. That's not why they really call it. It's a nice way to remember it, though. Secant line has 2 points. All right, so the slope of the secant line tells us the average rate of change. It tells you, on average, how much change occurred over that time period. Okay? But not an exact one, right? It's just an average. Now, on our homework, we did something a little bit different. Okay? We took those two dots, right? And what did we do to the second one up here? We brought it closer and closer and closer until they were approaching the same exact point, right? So, for people watching the video, they're not gonna be able to see this. But I'm gonna use this ruler and I'm gonna put it right on top of my secant line. Now I want you guys to tell me to stop when this ruler is only touching one point of the curve, okay? Good. So right now it's touching like probably right about here. You agree? Change colors here real quick. It was touching right about here, and my ruler looked something like that, correct? It's only touching one point, but that's still a straight line, right? And doesn't that line have a slope? So what that means is that's the slope of the curve at that one point. Now we talked about on the homework how you can't calculate slope using y2 minus y1 over x2 minus x1 if there's only one point, because what do you end up with? Undefined. But does that mean there's no slope? No. It actually is the slope of the tangent line. So we're going to call this a tangent line. And the slope of a tangent line tells us the, what do you think?
Instantaneous slope.
You got it, the instantaneous, and I'm going to call it rate of change, but yeah, you could say instantaneous slope technically. In other words, not how fast did the car go overall, but how fast is it going right at that specific moment. Okay, because the speed is constantly changing. And this point that we're looking at is what's known as the point of tangency. Point of tangency. All right. Now, what we saw from our homework was that even though we couldn't calculate what the slope was at that one point, we could estimate it, right? By approaching it. by finding the limit, right? We approached it. I couldn't find out what the exact slope was at 2, 4, but what I did was I made a secant line, and I let that get closer and closer to that point, and we saw that the slope approached 4, right? All right, so what that tells us then is that if we pick 2 points close enough to the point of tangency, we can estimate the instantaneous rate of change with the average rate. Lot to write there. I'll wait a second. But I'll say it again. If we pick 2 points that are close enough to that one point of tangency, then the slope of the secant line between those 2 points will be pretty darn close to the slope of that tangent line. Okay? In other words, we can estimate the instantaneous rate of change using an average rate of change. And that's what our homework was demonstrating for us. We kept letting those points get closer and closer so we could see what it was approaching. So, for instance, on this picture up here right now, the 2 green points on the end, they're not very close to that red point of tangency, are they? And you could tell by comparing the slope of that secant line and the tangent line, they're substantially different, correct? But what if I picked 2 points that were actually closer? Like, let's say I picked point 1 here and point 2 here and connected those with a line. Doesn't that pretty much almost parallel now? So the closer you get to that point of tangency, the better that your average rate of change actually gives you a good estimate of what your instantaneous rate of change is. Okay. Last class, somebody asked, well, how close is good enough? And there's no answer for that. But for you guys that are engineering, you know that there's margins of error that are acceptable and margins of error that are not. But in this class, don't worry, when we get to a question where I ask you to estimate using an average rate, you'll know the 2 points to use. It won't be a question of what. But there you go. So that's kind of the top. That's a big talk for what we're doing today. That's the concept. That's the idea of what we're learning today. Average versus instantaneous rate. The next thing we're going to talk about is what a derivative is and how to write them, and that'll take us to the end of the day. So let's go ahead and move on from here. All right, the derivative. The derivative of a function, let's put an example up here. Let's say we're talking about x squared. I'm going to use f of x though instead of y. The derivative of a function is another function. Do you guys remember what I told you the derivative of this was?
2x.
It was 2x. This is the notation we use for a derivative. So the derivative of a function is another function that tells you the instantaneous rate of change at any point. So 2x is the derivative of x squared. And 2x will tell you what the instantaneous slope is at any point. So at 2, what's the slope?
4.
What would the slope be at 3? 6. Okay, so that's a lot easier than using a table, right? So the derivative of a function is another function, which is f apostrophe x, which is called f prime. Let's write that down. It's called f prime. That can be used to calculate the instantaneous rate of change for any given value of x. And here's some more vocabulary for you down here. To differentiate, that's the verb to find the derivative. You don't say derive. It's tempting, but you don't say I want to derive this function. You don't say that. You say I want to differentiate this function. Okay? Derive means something else in English language. Next one. A differentiable function is a function that has a derivative on some indicated interval. Not all functions can always have a derivative. A derivative is a function that tells you the what?
The instantaneous rate of change.
Which is a fancy word for
The slope. at
the
any
slope.
point.
So is it possible for a function to fail to have a slope at a point? What does a function with no slope look like? A vertical line. Okay? So for instance, square root function looks like this, right? Well, the slope would be the slope of the tangent line at that point. So a tangent line at that point would just be a vertical line. It does not have a derivative at the end point. It's not differentiable. Okay? All right, so let's talk about reading mathematics. For any given function f of x equals y, the derivative is represented in the following ways. This is how you say it. The derivative of whatever the output is with respect to the input. Okay, you guys remember what output and input is? Output is, or input's what you plug in, output's what you get out. So in this case up here, for this function, what's my input variable? It's x. What's my output variable? Y. You could also say f. Okay? So, all of these say that. The prime symbol, that means derivative. So, the derivative of f with respect to x. The derivative of y with respect to x. The derivative of f with respect to x. The derivative of y, and it doesn't tell us what the input is, but since we know up here, we can assume that it's x with respect to x. Okay? They all mean the same thing. Just different ways of writing the same thing. Just like division can be written like this, or like this, right? You can write derivatives in different ways, and those are all the different ways they can be written. Okay? So let's practice saying some of these things, okay? I'm going to put one up here. I want you to say that. So don't say it yet. But here's Sam. How would you say that? Good. I'm not going to write it. I'm just going to say it. The derivative. Oh, that's interesting. The derivative of g with respect to m. Good. Let me ask Nate. Where's Nate? Hi, Nate. What's the output variable here?
Output is
Oh, this is Nate McClaskey.
oh,
Yeah,
yeah.
That's okay. Go ahead, Nate McClaskey. So what he said m, do you agree that that's the output variable?
No.
Okay. So you know how I remember this? The one that's on the inside of the parentheses is the input who's inside there. So that's the input. So output would be g in this case, we'll call it. And that's how you know which one comes first when you say it. It's the derivative of g with respect to m. And what that means is that m is kind of like the guy in charge. M is the one that's like, you better respect me. He's saying, when I change, you change. If I change this much, you change that much. Okay, he's the boss. So G is going to change when M does. And G's like, yeah, okay, I'll follow your lead. Go ahead. All right, let's go ahead and take a look at another one here. Go ahead and check with a neighbor on that one real quick. Won't give you quite as long this time. All right. Where is Samantha? Hi, Samantha. How would you say that?
It's the derivative of m with respect to
Good. Derivative in respect to t. All right, let's do another one. How about this? All right, now I'm coming to Nathan Cervantes. Now it's your turn, Nathan. How would you say that?
The derivative of y with respect to t.
Very good. Ryan, if I were to graph, well, first of all, what function are we finding the derivative of here, Ryan? Good. So we're finding the derivative of the function of y. Now, if I were to graph this, Ryan, what variable would I put on the vertical axis? That's right. And what would I put on the horizontal axis? That's right. Input goes on horizontal, output goes on vertical, right? All right. Let's go ahead and do another one here. How about this? How would you say that? That's a B. All right. What do you think, Brody?
The derivative of r with respect to b.
That's right. If I were to, what function? This is kind of a tricky question. Let's just do your best. Where's Alex? Oh, hi, Alex. What's the output variable here? I'm glad you don't think it's the D. That's good. No, the one on top.
R.
So it's R, which means if I was graphing this, R would go on which axis? The y-axis. Okay. So we have some function, right? R goes here, B goes here. I don't know what they represent. I was trying to make a story out of that, but I came up with something that was crude and inappropriate, so I didn't say it. So anyway, B and R, and we have a function, right? But what this is another equation, which we don't know what it is right now, but it's an equation that will tell us the slope at any point. Okay, that's what that is. Okay. So if I wanted to rewrite this as a function, you could do this, R of B, right? The output is R, the input is B. But as soon as you put that there, now it's a derivative, right? How would you write this one as a function? So the function's m of t, but the derivative of that is m prime of t. All right, so let's do another one. And this will probably be our last one for this set. I want you to do two things. I want you to tell me well, I'm going to ask a lot of questions. What's the input? What's the output? What axis is what letter? What's the original function? How would you write that in function notation? And I'm going to ask you to also say it. So, got all that?
Yes.
All right. So, go ahead. Okay. Alyssa, how do you say it?
The derivative of y with respect to t.
Good. Jade, what's the output? Uh-huh. Because I want to know. Just kidding. Y is correct. All right. Isaac, what's the input?
G.
Cool. Roxanne, how would I write the original function in this form here? It'd be something, parentheses, something.
Y parentheses t.
Good. If I were graphing this, Angelisa, which variable would I put on the vertical axis? There you go. Input goes on horizontal, output goes on vertical. All right, so there it is. And this represents the what of y? The derivative. The derivative is a what? Starts with F? It's a function that what? Tells you the instantaneous rate of change at any point. Okay? All right. So let's add a little bit more to the mix there. Move this thing up a little bit. Oops. Okay, so now we're gonna put a new thing in there. Like I told you, derivative is a function that tells you the instantaneous rate of change at any point, so long as you plug a point in, right? So now, if I actually put a number in there, instead of like just having an input letter in there, if I actually put a number in, now we're not going to call that the derivative anymore because it's not a function now. Now it's an actual answer, it's a number. And that means that's telling you what the slope is at that point. And we call that the instantaneous rate of change. So for any given function, f of x equals y, the derivative at a specific input value c is represented in the following ways. And they're all read in the same way. So if you actually have a number in here, like c represents a number, like let's say 2, f prime of 2, then you would say that is the instantaneous rate of change of f at x equals 2. Okay, so let's go ahead and write that. The instantaneous rate of your output variable at the number input that they're giving you. So in this case, they're all, what's my output for these? All of these have an output of f or y. You can say either one. And the input number in this case is c, right? But what's my input variable? It's still x, right? We're still plugging in, like the input letter's still x, but now we're plugging a specific number in, which we'll call c. C stands for constant, it's just a number. Okay, so I'll read them to you as I highlight things. Since there's a number, I'm not going to say derivative anymore. I'm going to say the instantaneous rate of change of f at x equals c. The instantaneous rate of change of y at x equals c. The instantaneous rate of change of y at x equals c. Okay? So, I would like you guys to see if you could write one for me now. Using this notation, I would like you guys to write the following. I'm only going to say it. I'm not going to write it. I want you to write this for me. I want you to write the instantaneous rate of change of g at x equals 1. The instantaneous rate of change of g at x equals 1. See if you can write the symbol. Still working on it? Okay, I'll give you a little more time. We're using this notation, right? We're going to have something here. We're going to have a prime. And then we're going to have something here. Now, what I wanted you guys to write is, what's the instantaneous rate of g at x equals 1? So my question to you would be, what goes here? And here? How do you know that it's x? How do you know that's an x number, though? Well, because I told you. I told you in the sentence, when x equals 1. Yeah?
Because that's the input, right?
Yeah.
So we don't put x.
No, not on this one. So I want you to write the same thing using this one now. I want you to tell me what the instantaneous rate of change of g at x equals 1 using the second one now. See if you could write that. Yeah?
That line is part of the equation?
Yeah. I've seen it. Sometimes they don't include the line, but usually they do have that line.
So if we didn't put it there, do you think?
I think it's best to do it, just so it's not confusing.
Oh,
Because it could actually be misleading in some cases if it's not there.
we use the same number, right?
Yeah, we're still doing the instantaneous rate of change of g at x equals 1. Check your answer with a neighbor. I don't know. All right, ready? Where's Jacob? Hi, Jacob. So, can you tell me what to write?
dt over dx, and then that line here, and then x equals 1.
You got it. The instantaneous rate of g with respect to x at x equals 1. Okay. Let's write another one. Do both of them this time. Yes, sir.
So on these ones, you have to put x equals 1.
If you didn't, then we're no longer talking about an instantaneous rate of change. What are we talking about now? The derivative. which is the equation that can help you get anything you want. But yeah. All right. So let's do another one here. I would like you guys to write both in both ways, okay? I want you to write the following. The instantaneous rate of change of L when t equals 5. I'll say it again, but you're doing it in both ways. The instantaneous rate of change of L when t equals what? 5. The instantaneous rate of change of L when t equals 5. Write it in both ways and check your answer with a neighbor. Hi, Brandon. So give me the top one here. How would you write the instantaneous rate of change of L when t equals 5? How would you write that for the first one?
L prime 5.
That's it. Good job. Nice. Juliana, how would you write the instantaneous rate of change of L with at t equals 5 for the second one? That line, yeah. I wish it had a better name than that, but that's its name. Okay, so let me throw some other questions for you. Ready? These are just going to be on the spot. Chris Ignacio. Hi. Oh, sorry. Too many new names, Chris. Sorry about that. All right, so Chris, what's the output variable for this? L. Zachariah? Is that right? Oh, hi, Zach. Zach. What's the input variable?
For t.
Yeah, good. Dario, what's the function? I'll give you a hint.
T.
Where do I put the t?
Inside.
Here?
Then you put L.
Good. The function's L of t. Good. Which variable would go on the vertical axis, Ashley? Where's Ashley? Hi, Ashley. L would go on the vertical. Good. Jennifer Castillo. Where are you, Jennifer? Hi, Jennifer. Does this represent the slope of a tangent line or a secant line? Because this is a what? Instantaneous rate of change, and that's a tangent. And that's okay, Jennifer, still get a point though. Emmanuel, where is the tangent line touching the curve? Where's Emmanuel? Hi, Emmanuel. Where is this tangent line touching the curve at?
It's touching the curve. The point of tendency.
Good. And what's the numeric value?
5, right?
It is 5. It's the only number up there. So we have a curve, and there's a tangent line. It's touching that curve at one point, and that's at the point t equals 5. And at that point, the slope is something. We don't know what it is, but that's what the instantaneous rate changes. So that's what all it is. So I'm just giving you guys the ideas here. We're not calculating anything. But let's move into that. So we talked about this function on our homework. And I told you that this function's derivative was what? And then I told you that when x equals 2, what was the derivative value? Okay, what number up here represents the instantaneous rate of change? What is, in other words, the slope of the tangent line at that point? The 4 is, right? So at x equals 2, the instantaneous rate of change of f at x equals 2 is 4. In other words, the slope of my tangent line at that point was 4. Okay? So we're just learning how to read math today. But if we have some time, I'd like to sneak into some of the other stuff. And we do have a couple minutes. So let's use those minutes. We're going to revisit this again tomorrow, though. So now, how did I know that the derivative of x squared was 2x? You're going to know that too by the end of tomorrow, okay? And it comes from these things that we call the derivative rules. And this whole chapter is just teaching you how to find the derivative equation for any function that I might give you. And there are just a bunch of rules. So let's talk about this one. The derivative of a constant function is what? What's the constant rule? So, does anybody think they know this? Well, not Ryan. But does anybody think they know what would the derivative be of y equals c? Like, for example, y equals 2. What's the derivative? It's not 2. I'll give you a hint. Think about what that graph looks like and remember what a derivative is. 0. Nice job. What does that look like when you graph that? It's a horizontal line, right? The derivative is an equation that tells you the slope at any point, correct? Well, what's the slope for that function everywhere you go? 0. So here's your rule. When you have just y equals a number, the derivative of a constant function is 0. Doesn't matter what it is. So if I told you x equals 3, I'm sorry, y equals 3, then what's the derivative? Y prime equals 0. Doesn't matter what it is. So if c is a constant, the derivative is always 0. All right? Question. Don't write this down. This is just for fun. What's the derivative of this function if we're thinking of the derivative of y with respect to x? Undefined. It's a vertical line, right? No slope. But that's it gets a little bit complicated. Because if I were to say to you, what's the derivative of x, then it's just another constant function. But if I say, what's the derivative of y, then it's undefined. If you're confused, don't feel bad. It's okay. We will continue our chat tomorrow. So